My name's Ian Smith from MIPI Alliance, and I'll be your moderator for today's session. So thanks for joining today's webinar. This is the first of 3 MIPI audio webinars planned for this week. In this 3-part webinar series, the leaders of MIPI's audio and software working groups will introduce the full portfolio of MIPI audio specifications, explaining the purpose and content of each specification and sharing their insights onto future developments. Today, we will start with a brief introduction to MIPI Alliance, and then we'll kick into our first main presentation of today, a primer session, which will offer a system-level overview and high-level introduction to all of MIPI's audio specifications and supporting software specifications. And then building on this today's session, tomorrow we'll have a specific session focusing on MIPI SOUNDWire i3S, our latest new specification just released last week, hot off the press. And then on our third session on Thursday, we'll focus on MIPI's audio supporting software specification and tools. So 3 sessions this week, and I'm sure you'll find all 3 of them very, very informative. Okay, to start today's session, I'll give a quick overview of MIPI Alliance before I hand over to our main presenters for today. So MIPI was founded back in 2003. It's a member-led, not-for-profit industry alliance, and it started by defining the camera and display interfaces within the mobile phones of the day. Obviously, MIPI picked the right industry to work within, because obviously the mobile phone industry has expanded massively since 2003. And if we look at where MIPI is today, MIPI is everywhere. We have expanded our portfolio of interfaces. There are over 50 current MIPI specifications in active use. Whilst MIPI's roots were in mobile, MIPI interfaces are now being used in automotive, in laptops, PCs, virtual reality headsets, basically everywhere. And you can see here some of the most recognized specifications that many of you, I suspect, are familiar with. MIPI CSI2 for camera, MIPI DSI2 for display, MIPI SOUNDWire for audio, all the in common use across mobile and beyond. We have RFFE for RF front ends, MIPI I3C, a command and control interface that's rapidly growing in support across the ecosystem. And all of these are complemented by a comprehensive set of MIPI physical layer interfaces. I'm sure many of you are aware of C and DFI, used for camera and display, and a more recent MIPI A5 for long reach automotive applications. Over the last 20 years, obviously, MIPI has been adopted into billions of devices. And a lot of what underpins this is MIPI's usage rights, which are granted royalty-free to all MIPI members. Okay, so that's my very quick introduction. In fact, there's one more slide, actually, just to talk about the ecosystem. I mean, the MIPI membership covers not just the mobile ecosystem, it covers consumer electronic ecosystem, automotive ecosystem, the PC laptop vendor ecosystem. It's incredibly broad now, covering all bases. We have over 375 members covering at least 30 countries. It's expanding all the time. So yeah, if you're not aware of MIPI, you are now, and you're welcome to join us and contribute to the future of our specification development. Right, well, that's probably enough from me. Let's get to the main event for today. Let me introduce today's speakers. I could probably spend 10 minutes going through their CVs, but nonetheless, we have 2 world experts here in terms of MIPI audio interfaces, and they're going to share their expertise with us today. First up, we have Aruni Nelson, Principal Engineer at Intel Corporation. Aruni is currently the chair of the MIPI Audio Working Group. She also holds many, many other roles within the MIPI Alliance, too many to mention here. And we have today also Neil Warren, Technical Consultant at MIPI Alliance. Neil was a long-standing former chair of the MIPI Audio Working Group and brings many, many years of industry experience with him today. Okay, let me hand over to our experts, and I'll let them take today's presentation forward.
All right, thank you, Ian, for setting up the stage with what we do in MIPI. We will now look at what MIPI does in the audio space. And as part of that, today we will look at some of the audio interconnects we have defined in MIPI. We will also look at some of the supporting audio specifications we have developed, some upcoming specifications, and we'll also talk about some of the tools we have developed related to these audio specifications. And then we'll end our session with Q&A. So let's see what we do in the audio space. And this slide here illustrates a high-level view of the audio subsystem stack. And as you can see, the MIPI logo appears across several layers, representing the range of specifications developed within MIPI that address different parts of the audio stack. And MIPI specifications are designed to support not only the hardware integration through standardized interconnect definitions, but also system integration by providing the mechanisms that can make platform details accessible to the operating system. Now, if we look at the audio interconnect itself, the MIPI Audio Working Group has been focused on addressing the limitations of legacy interconnects like I2S, TDM combined with I2C. And over time, this group has continued to evolve the audio interconnect architecture. We began with SLIMbus specification, then advanced to SoundWire family of definitions, and most recently, we introduced the SoundWire I3S or SWI3S specification. We will dive a bit deeper into these interconnects shortly and look at SWI3S in detail in tomorrow's session. But in essence, these SWI3S and SoundWire specifications, they define the interconnect and how communication occurs between the managers and the peripherals on the interconnect. And it describes the expected behaviors of each component on this interconnect to ensure seamless interoperability. Then we have the managers and controllers that operate these links or interconnects. We are currently defining a unified audio bus controller interface, which allows the host system to manage one or more managers, their buses, and the connected peripherals. And this specification outlines how the managers and controllers should respond to the commands or instructions from the host and how they relay data, status, and event information back. And then we have the peripherals with specific functions themselves, like the microphones, the amplifiers, and other audio devices. The SDCA, or the SoundWire device class for audio specification, defines their control mechanism, or the knobs, standardizing how these devices are configured and controlled. And to bring this all together, say your system firmware such as BIOS, it must be aware of the hardware configuration. So the appropriate firmware and software components can be loaded at the right time, whether that's during pre-OS or post-OS initialization. And our MIPI discovery and configuration, the DISCO specification, defines how these device properties and configuration parameters are described, ensuring that any operating system can correctly identify and interact with this hardware. So with this standardized foundation, operating systems such as Linux, Windows, and other OS operating systems, they can build their audio stack in a consistent way across different platforms and applications. And in addition to these specifications, MIPI also provides tools to assist designers and integrators during design and development, including utilities like the SWI3S visualizer tool and the DISCO tool, helping these engineers evaluate, prototype, and validate their designs early in the process. So now that we have looked at the overview, let's see what we are doing in the audio interconnect space. And as we all have seen across industry, technology advances in response to new needs, emerging use cases, and ever-evolving requirements. And the same holds true for our audio interconnects. They have continued to grow and adapt as devices, performance expectations, and power efficiency demands have changed. And MIPI's audio working group has continued to push forward, always looking for the next improvement, the next level of efficiency, and the next generation of designs. And this slide here shows exactly how we have evolved the audio interconnects, starting with SLIMbus. MIPI released the first revision of SLIMbus, the serial low power interchip media bus, back in 2008. And the motivation behind SLIMbus was to overcome the limitations of older audio interconnects and to meet the growing demands for high quality, multi-channel, multimedia in mobile devices. Older interconnects were designed for simpler systems. They used point-to-point connections. They supported limited channels. And to scale up, engineers had to use multiple separate buses, which increased board complexity, pin count, and power use. So to solve these issues, we created SLIMbus with the key goals in mind, like reduce pin count, combine audio and control data, enable scalability and flexibility. And SLIMbus was a huge step forward. It unified the audio and control communication, it streamlined design, and it paved the way for more intelligent low-power audio systems. But there was more to be done, and the team wanted to build on the foundation that SLIMbus had laid to make the interconnect even more capable, more flexible, and more power efficient. And as you can see from this Venn diagram, SoundWire carried forward many of the strengths of SLIMbus while adding new capabilities. We added dual data rate operation, direct register accesses, more control over the audio link, clock pause for low power modes, peripheral initiated wake requests, things like bulk transfers for use cases such as firmware download. And first revision of SoundWire specification was published in 2015, marking the next major milestone in MIPI's audio journey. And as I mentioned earlier, there's always room to make things better, more efficient, more elegant, and more adaptable across devices and form factors. And that's exactly where SWIS or SoundWire i3S comes in. SWIS builds on the solid foundation of SLIMbus and SoundWire, but it takes a significant leap forward in performance, in scalability, and design flexibility. SWIS also offers a two-pin interconnect, but it supports both single-ended and differential PHY types while maintaining a unified protocol and software layer, which is a huge advantage for system integration. And with support for differential low voltage PHY, the bus can operate at voltages as low as 50 millivolts and reach up to 2 meters. And over these two pins, SWIS delivers up to 76 megabits per second of bandwidth. But what really sets up SWIS apart isn't just these bandwidth numbers, it's the flexibility and robustness of the design. SWIS brings more refined power control. SWIS also has, it has taken the what SoundWire defined in terms of link power state, it has taken it further. It defines peripheral low power states as well. And the synchronization in SWIS is also far more flexible. Instead of being restricted to frame boundaries, like in SoundWire, SWIS allows sync events at row boundaries and across multiple devices or across data ports within a same device. And this gives designers the fine-grained timing control, and it supports complex multi-device synchronization, which are crucial for applications, say, like multi-mic arrays or phased audio playback. But other than that, SWIS also strengthens the control channel with built-in CRC protection, robust token handling, error counters, moving well beyond the parity-based approach which was used in SoundWire. And from encoding standpoint, SWIS uses 8B, 10B encoding for control data bytes, and NRZS encoding is applied to the bits within these bytes. So in summary, SWIS is not just an incremental improvement. It represents a transformative advancement. It is faster, it is quieter, it is more scalable, and far more intelligent in how it handles data, synchronization, and power. And with that, let me hand off to Neil. He will provide some more details on SLIMbus and SoundWire, and then we'll take a look at SWIS a little bit more.
Yeah, drawing your attention to, thanks to Rooney, drawing your attention to the bottom diagram here, you can see a typical SLIMbus device with a single required pair of clock and data. More data lines can be used if peak bandwidth requires it, but that was rarely done in systems. So SLIMbus is a global bus of those 2 wires connected to all the audio devices. But SLIMbus supports logical connections, as shown on the top right. So a bus that has full physical connectivity could have this kind of logical connectivity. And SLIMbus conveyed both audio and control information over these 2 lines, saving a lot of pins, as Aruni mentioned. It also enabled phone makers to add DSPs into existing audio reference designs. This was crucial for some of the targets that the telephony carriers required for a few years, allowing a DSP to get in the loop between the microphones and the SoC to do noise suppression. SLIMbus has a gear shifting mechanism to raise and lower the clock by powers of 2 in order to make a trade in power versus bandwidth. Even though the specification provided for an audio quality clock to be delivered over that clock line, that rarely occurred in systems. We think that was because we were not very specific about that. And so it was an exercise left to the reader, how you would cross the clock domains, etc. And in SoundWire Classic and SWIS, we think we've addressed this by well specifying that so that you really can count on the buses to deliver that clock. SLIMbus also had an allocation scheme with a linear allocation scheme by allocating nibbles to various uses. Moving on to SoundWire, which is now an older interface for MIPI. SoundWire similarly uses 2 pins for clock and data, but it lowers the power by being DDR. So that is, useful data is transmitted on each clock edge, not every other clock edge, as the SDR SLIMbus and TDM and other existing interfaces does. Classic allocates bandwidth in a frame using bits. So we can get essentially a factor 4 lower latency than SLIMbus, approximating the latency of a PDM bus. SoundWire Classic also supports higher control bandwidth than SLIMbus, naturally in the way the protocol is defined, but also via a bulk mode. So if you're using the bus for a firmware download for a DSP, maybe in your speaker amplifier or maybe just an existing DSP, the boot time or any kind of parameter change can be much faster. Classic also supports a finer grain trade-off in power between power and bandwidth. So it uses a 2-dimensional allocation scheme like Sonnet. So you can change the number of columns per row as well as the row rate, again, synchronously, so that you could be having seamless audio flow while you're making these changes in bandwidth, but it's finer grained than SLIMbus. Similar to SLIMbus, Classic does support multiple wires. This particular diagram is showing 2 separate buses that you might have done for systems that are very aggressively managing power. Okay, back to you, Rooney, for the newer thing.
All right, let's look at SWIS a little bit more, the newest audio interconnect in MIPI's family of audio interconnects. So SWIS defines a 2-pin multi-drop interconnect that carries control, data, interrupts, and synchronization all on the same pair of wires. And as mentioned earlier, it provides higher bandwidth up to 76 megabits per second, which is more than 3 times of what SoundWire offers over 2 pins. And SWIS gives you more number of data ports, more channels, richer audio formats, and tighter timing alignment across complex audio systems, all while maintaining a low-power, deterministic transport mechanism. And each SWIS link can connect up to 12 peripheral devices, things like microphones, amplifiers, codecs, or haptics controllers, all managed from a single host through a manager node. And one of the big differentiators of SWIS is its efficiency in both power and design. It consumes less power in normal operation, even with multiple peripherals being active. And it supports link lengths, as you mentioned, up to 2 meters, And that range opens up new possibilities, especially for devices where components are physically separated, such as in, say, automotive infotainment or distributed speaker systems. And from a physical layer perspective, as we mentioned earlier, Swiss supports both single-ended and differential low-voltage PHY options, and that's a major advancement. The single-ended PHY targets ultra-low-power applications, while the differential PHY enables robust communication with lower operating voltages, extending the reach and providing excellent noise immunity. And together, they give designers the flexibility to scale the same interconnect across small wearables, laptops, and even large embedded systems. Even with support for both these PHYs, the control and software, the protocol and the software layer stays the same, saving both the development time and validation effort. Swiss also employs data scrambling techniques, which minimizes crosstalk, and it reduces deterministic EMI peaks, which is a huge advantage. And Swiss also cuts the link bring-up time dramatically down to around 6 milliseconds compared to up to 33 milliseconds with SoundWire, which helps in enabling, say, faster device initialization and reduced latency at startup, which is great for systems that need quick resume or always-on responsiveness. So in short, Swiss delivers a powerful combination of speed, scalability, and efficiency, which are designed to meet the complexity, the density, and performance requirements of today's and tomorrow's audio systems. So now let's see how would one integrate these interconnects or buses in a system. So we have these interconnect specifications, the Swiss, the SoundWire, they define the bus itself and what the manager and the peripheral need to do and how this bus works. But how is it integrated into a system? How does or how can the host system hardware or software communicate with these managers to work with the interconnects they manage and the peripherals that are connected on these buses? And we are currently defining a MIPI audio bus controller interface, which defines the hardware and the software interfaces that are exposed by an audio bus controller, which can be used by the host system to communicate with, to configure and synchronize these multiple managers and peripherals across different audio buses. Now, this is similar to the host controller interface that we are all familiar with. And as we know, we don't have a standard host controller interface specification for any of our MIPI audio buses today. So this specification defines a common programming model. So whether the system uses one SoundWire link or multiple Swiss links or even older audio buses, everything can be controlled and monitored through a unified interface. So if you look at this diagram on the slide, at the top, we have the host system, which can be running the operating system, power management framework, and driver stack. And it communicates with the audio bus controller through an implementation-defined bus or fabric that could be, say, PCIe or APB or another system-specific interconnect. And inside the audio bus controller, we have a common hardware interface, a common register interface, and multiple manager interfaces, each corresponding to an audio bus type. And then each manager has its own set of peripherals connected via its respective link. And the audio bus controller coordinates them all. One of the key functions of this specification is to define the capability of discovery and configuration. So when the system boots up, the host can use the audio bus controller interface to discover how many managers are present, identify their bus types, and then enumerate the peripherals attached to each bus. And once all the managers, buses, and peripherals are discovered, then the host configures each manager's, its peripherals using the same unified command structure. And the specification will also define how the host system can access both the control plane and data plane of the audio buses and the components that are connected to them. Synchronization is another key capability which we will be defining in this specification, which will provide the mechanism to perform different types and scopes of synchronization. For example, clock synchronization, ensuring all managers and peripherals share a coherent timing source, command synchronization to coordinate control commands so that configuration changes happen deterministically, transport stream synchronization, aligning audio data streams across links or devices. And the scope of synchronization includes across multiple controllers, across multiple managers, across multiple data ports within a manager. So scope can be narrow or wide depending on the use case. Beyond synchronization, this specification also defines a structured way to manage events, interrupts, and handle errors. And another key aspect that we are defining as part of the specification is the power management, which will work hand in hand with the operating system's power policy manager to control these managers, peripherals, and buses based on the system policy. So now we have seen our audio buses and the interface to the controller and managers to manage these buses and the peripherals which are connected on these buses. But a system needs to know what is really connected and what function these devices provide, and some means to control these functions based on the use case and application needs. And on this slide on the left here, we have a high-level block diagram showing different audio devices performing different functions. And these are connected to a silicon on chip. And MIPI SoundWire device class for audio specification is a standard for host controllable audio devices that connect via a MIPI SoundWire family of audio interconnects, making it easier to develop generic software for these audio devices like microphones, amplifiers, which can be used across different platforms without needing to write unique software for each hardware component. And this specification is applicable to any system topology that uses MIPI SoundWire family of interconnects. So this SDCA specification is a complementary specification. And we will talk more about this in day 3 of this webinar session. Now, from a systems perspective, as I boot my system, there are necessary initializations that need to happen before we boot to the operating system. Some pre-OS buses, some pre-OS hardware drivers, and some services need to be initialized before we boot to OS. And a couple of well-known frameworks such as ACPI, the Advanced Configuration and Power Interface, and device tree are used in systems to describe the hardware configuration. And they enable the operating systems to interact with these hardware. For example, Windows relies heavily on the ACPI for hardware discovery, configuration, and power management. Windows interacts with these ACPI tables, which are provided by the system firmware, such as BIOS or UEFI. And these tables describe the hardware resources and the capabilities. And then another popular operating system, Linux, it uses both ACPI and device tree. For systems with UEFI firmware, Linux reads the ACPI tables for hardware configuration and power management. And on ARM and RISC-V based systems, Linux uses device tree to describe the hardware layout. MIPI discovery and configuration specification for audio uses a framework built on ACPI to standardize how the operating systems detect and configure these audio components. So on the left here, we have an example ACPI-based system where the device-specific data, DSD, can be read through the probe operations. So from a developer creating a device using MIPI audio components, the process would be something like the manufacturer of the audio component, say like codec or amplifier, they provide a description of the device's capabilities in ACPI source language, for example, as specified by MIPI Disco for SoundWire. And then the system integrator will incorporate this ASL into systems firmware such as BIOS. And when the device boots, say any ACPI compliant host operating system reads this ASL from the firmware, and then OS uses this information to identify the type and capabilities of these audio devices. And then it'll automatically select and load the appropriate generic driver, eliminating the need for vendor-specific drivers. So this standardized process dramatically reduces the development time and cost, as the system can configure a wide range of compliant audio devices without requiring extensive custom driver development. And again, on day 3 of this webinar, you will hear more about DISCO specification. So far, we have seen how the standardized audio buses, device functions work, and the interface through which the host system can reach and control these audio bus managers, the audio buses itself, the peripherals that are connected on these buses. But the implementation of the audio systems varies from system to system. And there is currently an ongoing effort in MIPI's software working group to standardize the streaming interface for different audio subsystem designs within an SoC through the audio portal specification. And here on the left, we have indicated where the audio portal hardware and or software sits and how it's connected to the audio bus controller. And again, you will learn more about this on day 3 of this webinar series. So now we know how we have everything we need to build an audio system with MIPI defined audio buses. But what about debug? How can I debug these devices that are connected over the Swiss link? In MIPI, we have debug working group, and we are defining a specification which can use Swiss link to debug devices that are connected over this link, the debug over Swiss specification, which will provide mechanism to perform closed chassis in-band debug of one or more Swiss devices that sit on this Swiss bus. And it utilizes Swiss bus capabilities, and it utilizes MIPI-defined standard debug protocols for sending the debug requests and receiving the debug responses. And you can do both, whether it is a run control like debug or collecting traces, you can do both. And on the left here, we have the stack diagram from debug specifications. And the whole debug stack just utilizes what Swiss has to offer in terms of transporting any data over the bus. And that is used to send these debug requests and receive the debug responses. And if you need more information here, please reach out to MIPI team members and we can get you plugged in for right information. So with that, let me hand over to Neil to talk about some of the tools which MIPI has developed to help the designers and system integrators.
Thanks. Here I'm showing a tool that was written by one of the system OEM companies participating in the audio working group. We call it the visualizer. It shows the mapping from the transport parameters that get poked into the hardware registers. That's up at the top, this array of numbers, to the bits on the bus and how things get allocated and where they flow, should you be looking at it with a logic analyzer. This allows engineers to experiment with traffic patterns, work out latency, bandwidth, allocation details, etc. The tool supports both source and sync ports at the same time to show how the bus is being used for fan-in or fan-out. Fan-in and fan-out are supported at multiple levels in the MIPI audio stacks. Here you can see on the very top right, data port number 3 in green is fan-out. It's data coming from one device. The green top of the bit cell is the source, and then you have 3 different syncs. So that's an example of fan-out. And then drawing your attention to data port number 4, that lovely teal. In the middle of the arrays of bits, you can see that teal is the receiving port in cases coming from 3 different peripherals showing the fan-in. I'm going to zoom in a little so you can see this is the array of values on the top. This is the data that an engineer would enter. The tool is used to fill in bits currently as they be poked into hardware. There's a flag in the source code if you want to change the UI to be more naturally encoded for people that think that way. But here I'm running with the flag set to the actual hardware values you would have written into the different devices to get the behavior as shown in this diagram here, where I've zoomed in on the traffic. This showing a hypothetical system on the left where we have the data coming from the microphones. You can see each microphone gets an opportunity every row to transmit. Here we're probably running at 3.072 megahertz row rate. So you can see the latency is quite low, on the order of 300 nanoseconds for those microphone signals. Going over to the right, the far right, that's data going out to the amplifiers. It's likely 2's complement, could be 1's complement if you wanted to save a few more microwatts. That encoding would be described in the disco data that Aruni just mentioned. And then show in the middle, maybe you have some data coming back from those same amplifiers, either a reference signal or a current and voltage measurement or what have you. This tool is open sourced and maintained by audio working group members at the moment. And then the last tool I wanted to show you was, we have Aruni had mentioned that once the system is booted and read the device ID and manufacturer ID from the device, and a few bytes, that's all that's required, then it can go look up all the data for that device in the ACPI tables. Well, we have a Disco tool that allows editing of those tables. An OEM might be using this tool to cull down the device's features and publish just those desired features in the final product's ACPI tables. This is also maintained by members in the software working group. Back to you, Aruni.
Okay, so I'm hoping that from this presentation today, you can see how MIPI and MIPI Audio Working Group is committed to not only advancing the audio technology to meet the needs of current and future audio systems, but we are also committed to making sure that these technologies can be easily integrated into any system, big or small, by addressing the need of every layer in the hardware and software stack up to the operating system audio stack. So there is still a lot of work going on there, and hopefully it'll help the system integrators and designers to incorporate these MIPI audio technologies in their devices. And with that, I think we can open for questions, Ian.
Yeah, thanks, Aruni. I think there's just one slide just to pop up, and that's just the sources of further information slide. Several places you can go. Obviously, the website is a good starting point. The MIPI technical brief there, you can actually, if you're live, attending this webinar live, you can get that from the handouts. You don't need to go to the website, but if you're viewing on demand, then you can use the link to find that document. And obviously lots of other resources here available for you. If you can't find what you need, then obviously reach out to the MIPI team admin@mipi.org, and we'll help guide you in the right direction. But yes, let's get on to Q&A. So we had a couple of questions in the chat. If you're holding on to any questions, now is the time to enter them. But let's take the couple of questions that came in, do them in reverse order. So the first one, I'll put it up on the screen here for the live people, but I'll read it out as well just for the recording. Are SDCA and Disco more targeted at the PC space, or do you see them being used in embedded systems as well? Aruni, Neil?
I'll take that if that's all right. I would see it being, it depends on your embedded space. So if you are buying a single model microphone or a single model amplifier for your product, then you might very well hard code everything in your firmware. But if you wanted to multi-source so that you could, based on availability of parts, switch between, a Texas Instrument amplifier and a Cirrus Logic amplifier or whomever, then you might want to have Disco data give you that. And so that's where that becomes more useful. Also, independent of whether you actually take advantage of it in your software, the specifications coming out of software group are very detailed about features and behavior. So it's kind of a lingua franca or a standard way to show that information. So I think for system integrator, you're not getting each vendor's unique language on how they describe the features. It's kind of a MIPI defined way to describe the details of your device. So I think it just makes it easier to parse through all the data when you're looking at data sheets. David, does that answer the question?
David, if you've got a follow-up question, type it into the box and we'll come to that. Yeah, there we go. Great. Okay. So the other question we had was specifically related to slide 22, which I will through this clunky system, I can't go straight to slide 22, so I will flick back in series here. And there's the question, why are you showing PDM microphone and not Swiss interface microphone?
So that is just a miss. It is not that the Swiss microphones cannot be connected. We just took a picture from the specification and put it here. But you will have Swiss microphones connected, and the SDCA will work with that as well. So it's nothing to do that it is only limited to PDM microphones. I hope that answers the question. It's just a diagram, example diagram.
Okay, Nicolai, hopefully that answers your question. If it doesn't, then please come back with a follow-up. Okay, we have another question here. Let's get it up on the screen. Swiss was described as being quieter compared to earlier SoundWire. Does that mean less EMF radiation? Who'd like to take this one?
Rooney, you, me?
Either one works.
Okay. So in Swiss, in the differential mode, we've got a lower voltage swing. So going from 1.2 volt swing to 0.9 volt swing down to 50 or 200 millivolt swing, something like that, reduces emissions quite a bit. But further, it's differential. So once you get more than a centimeter or two away from that pair of wires, you've also got some cancellation there. And likewise, since it's differential, any current due to the protocol through the ground is reduced. So those are the reasons we're saying yes. It's much less of an aggressor on any radio system you might have in your product. So that's what we mean by quieter. Well, and I guess another way is some audio interfaces where the audio is encoded natively on the link ends up leaking into other audio devices on the bus. And in Swiss, we have a scrambling standardized so that we've essentially removed any content below 6 kilohertz that might leak into your audio devices. So those are the two ways it's, quote, quieter.
Yeah, both susceptibility and emission is, it's better with Swiss. So.
Okay, thank you. Yep, Scott, that's answered your question. Thanks for the confirmation. I have another one here from Raquel. What is a typical area overhead for an audio amplifier to be SDCA compliant?
SDCA, that's thank you for being that specific. The SDCA does not require any additional work. SDCA is all data that's in the host BIOS or ACPI tables, etc. All devices are required, regardless of whether or not you use the SDCA, to show their manufacturer ID and their device ID. So between the manufacturer ID, which is 2 bytes, the device ID, which is 2 bytes, and then there's one more byte required, that's version information. You're required to essentially have 5 bytes of ROM in your device. That might be very well just fixed with gates, or you might have some pins to strap things, or you might have a couple fuses if you have a single die that you're using to make multiple products with various features. But I think I gave you the example of the overhead's quite low, on the order of 5 bytes of ROM.
Thank you, Neil. Okay, well, getting quite a few questions coming in here. There's a thumbs up from Raquel there to the answer. Thank you. Next up, Nicolai again. Could you please share some success stories of adopting Swiss in consumer electronic systems where advantages of the bus really shined? That's an interesting question. Rooney.
It is very interesting question, and the reason it is hard to answer that question this week is because we released the specification just last week. But having said that, the audio working group members, several of them, and I don't think I'm the right person to reveal their names, but several companies have been working on implementing this, whether it's PHYs, whether it's microphones, systems, devices. They have all been working on it as the specification development has been progressing. So there is a lot of movement and uptake there. And some of those folks will start announcing their devices soon. So stay tuned and see what's available IPs are available for SWI3S which was announced from RSM. They have both manager and peripheral IPs. And similarly, other member companies, they have been working on IPs and specific SWI3S devices. And if you want more information, you can either reach MIPI marketing team, or you can join the MIPI audio working group and see the players there, and you can reach out to them. I hope that answers.
Thank you, Rooney. Neil, did you want to add anything? No? Okay. Great. Okay. Okay, next one. I'm not sure if this is a question or a statement. Again, from Daniel. I guess this will help with the following situation. We investigated an application where we want to install 6 SDW smart amplifier functions on a single SoundWire bus. Bandwidth is there, but we had to use 2 SoundWire masters as we couldn't get enough signal integrity. So I guess maybe this is a justification for. Yeah, go on, Neil.
Yeah. So SoundWire Classic requires that every single bit, all devices see the exact same value, because every device is responsible for checking parity for all of the bits on the bus. And in every single bit, the device that previously owned the bit must stop driving. There needs to be a little bit of dead time, and then a new device takes over. And then there needs to be enough time for that to have satisfied the setup time for all the devices on the bus so they can all see it. So there's, for each, the bit time needs to be quite long to allow all of these things to always occur in every bit. Whereas SWI3S, whether or not you're handing off from one device to another, is set in the way you allocate the data. So you actually explicitly allocate the handovers in some of the PHYs. So you only need to do that handover when it's required. Further, in SWI3S, you only need to reliably have communication from the manager to the peripherals and the peripherals to managers. If you want to have peripheral to peripheral communication, then depending on your bus layout, you'll allocate time or bits appropriately for that, either by adjusting the aperture or scheduling your handovers appropriately, or even using wider bits if needed. But that's a very long-winded way of saying in SWI3S, you have much finer control of how the time is allocated, and that's how we're able to push up the peak bandwidth, exactly for uses like you mentioned. That came from an observation of classic systems where we were. Other people were having the same trouble you mentioned.
Great, thank you, Neil. Okay, let's move on. Questions coming thick and fast. Being differential, does that mean there are 2 conductors for each clock and data?
I'm going to zoom back in the slides to see. What luck. So, man, this is showing a typical row. Let's see, I guess I'll start near the right side where the data is going to the amplifiers. And then you notice at the very end of the row, there's something that says S0. That is an abbreviation for sync 0. That is where the manager drives a 0 on the bus. And then the very next bit that's going to occurs over far on the left. That's S1. That is a rising edge. So every row, there is a rising edge that comes from the manager, and there are requirements in the specification about the jitter. So that is the clock. So each row, there's a clock edge, and there you go. So there is only one pair of wires for both clock and data.
Okay, next one up. So is SWI3S mandatory to be a low power device, e.g. low leakage power when power off with clock and data active?
I'm not sure what the question means in terms of, is it mandatory to be a low power device? Because what we have in the specification is it allows you different controls in terms of whether you can put the link in low power, bring it back up, and you can put peripherals in low power in the dormant state, and those peripherals can come back up and wake the system. So depending on the use case of your use case and your needs, you can utilize these knobs and hooks to make sure that you are a low power device. Neil, do you want to add anything more?
I guess you might be also asking about whether the ESD protection circuit is ground only referenced, also sometimes called as failsafe. So we do recommend it, but we don't require it. So you still are allowed to build a device that uses a diode from one of the pins to VDD on your part, which would be problematic if you're going to withdraw power from that part. If you're a system integrator that wants to aggressively manage power, then you need to be telling your device makers that they need to do something smarter on their ESD protection so that you can do that. Is that? Did we get it?
Okay, I'm going to put up the next question from Stanley as well. Maybe this is kind of a follow-up. Besides, regarding the low leakage device, are there any resource that we need to leverage to ensure fine SI operating well, not to interfere with other active devices?
I don't know of any resources. I mean, in regard to leakage, the specification is pretty clear and I think quite generous, although different people have different opinions. But what else?
I think the protocol itself is defined in a way where the handovers and who's talking on the link, the protocol is robust enough to make sure that we don't interfere with the data that's coming in from any active device. But that's at the protocol layer.
Yeah, there's a clarification. So the case that he's specifically wondering is one of multi-drop power off, but other devices active.
Yeah, so
clarification.
This is taken care of through the way the handovers are done between the devices that want to communicate on the bus, and the protocol takes care of this. And if you need more information, we can point you to specific chapters to refer and see how this works.
Okay, thank you, Rooney. So this may be our last question. We've got a couple of minutes remaining, so if you do have any, if you're holding on to a question, now's the time. A question regarding Linux. In Linux kernel, any SoundWire related developments? Are there any SoundWire related developments ongoing?
So absolutely. Intel did a great job of upstreaming to the Linux base support for SoundWire, as did Qualcomm. So there's driver support, manager support for drivers, and good example device drivers, all not using SOF that exist in Linux. And Intel did a really good job of a rich set of attributes to allow you to describe a lot of things that were common for devices that were being built for SoundWire Classic. So yes, there was significant development, and it's rich. Actually, I guess I should say I am unaware at the moment of any ongoing development, but maybe it's not needed because I think Intel and Qualcomm did such a thorough job as SoundWire Classic rolled out.
Okay, thank you, Neil. Okay, so I think we've answered all the questions submitted. Again, if you're holding on to a question, we've already got around 3 minutes left. I'll ask one of my own. And I guess the question I'm kind of expected to get asked is, does MIPI SWI3S replace MIPI SoundWire?
So the replacement is necessary due to the increasing demand of the embedded audio in modern devices. As it is expected that SWI3S will rapidly replace most of these legacy interface, at least in this decade is what we are hoping, but it is going to be a gradual process. It's like with any other technology. So it'll take a bit of time, but gradually and eventually SWI3S will replace other interfaces. At least that's what we hope.
Yeah, it's just that time scale, I guess, that is undecided, but it will take some time. Obviously, there's I guess a huge ecosystem around SoundWire at the moment that will last for some time. Okay, perhaps one last question from myself, and then we'll wrap up. And I guess it's kind of the obvious moderator question. If you could give one piece of advice to somebody looking to get started with MIPI audio, what would be your kind of golden piece of advice? Perhaps Aruni first, and then we'll Neil.
I think attending this webinar is a great start. If you haven't looked at the content, or if you didn't attend the webinar, then you can always look at this content later on. We wanted to give you an overview of all the audio specifications we have been developing, for what purpose, and then folks can choose the relevant specification based on what they're building. And apart from that, once you've figured out which specifications are relevant for your product, pick up that specification and read the overview chapter. The overview chapters always help, and then you can dive deeper into specific content, and you can figure out the details from there. I think that's the best advice I can give, but maybe Neil has something more to add.
Yeah, I was going to say, join MIPI and help make sure
Yes.
the specification as it evolves meets your needs. We are right now adding support for hubs and networks. We'll call it hubs and tiers, I believe. Some people might call it low-level bridging. But anyway, so the specification will continue to evolve and meet system integrate a wider range of systems. And so there's plenty of work to do. You can join us.
Yeah, please join. Okay, so I think we're at time. Yeah, thank you, Aruni. Thank you, Neil, for presenting today. Our first session in this webinar series. Really appreciate that. Been a really great session. Thank you very much to our audience for tuning in today and listening. We've had a huge number of people on the webinar today, so that's great, very encouraging. Obviously, today was just part one of our three-part webinar series. Please come back tomorrow, same time tomorrow. Where we'll have Neil, Aruni, and Christian presenting much more detailed, maybe not deep dive, but certainly to the next layer on MIPI SWI3S to find out more about this latest specification. That's a good place to tune in tomorrow. And then on Thursday, we'll have Devon and John walk us through all the supporting software specifications and tools. You've heard the brief overview of those today. So if you want to find out more about our software, rapidly expanding software set, please tune in on Thursday. Okay, I think we're done for today. So thank you very much, everybody. I'll leave you to get on with your days. Thank you.